We find ourselves suspended in an ocean of stars, adrift in what we have been taught to believe is an infinite expanse, a cosmos without boundary or terminus, stretching outward in every conceivable direction into distances that dwarf the capacity of human cognition. We are told that space extends forever, that beyond our small planetary home lies an unending procession of worlds and suns and island universes, each separated by gulfs of emptiness so vast that our minds cannot hold them, cannot process them, cannot translate them into any framework of understanding rooted in our terrestrial experience. This is the story we inherit, the cosmology handed down through generations of astronomers and philosophers and dreamers who have gazed upward and asked what lies beyond. And yet, when we ourselves look up into that same sky, when we direct our eyes away from the familiar constellations and into the deeper territories between the stars, we do not witness an endless luminous tapestry. We do not see a sky ablaze with infinite light. Instead, we are confronted with something altogether different, something unexpected and profound. We see blackness. We see void. We see absence. This darkness is not merely the space between stars. It is not simply the shadow cast by nearer objects blocking more distant ones. It is a fundamental feature of our perception, a boundary condition imposed not by the universe itself, but by the limitations of our vantage point within it. That blackness, that void which seems to swallow everything beyond a certain depth, represents something far more significant than simple emptiness. It marks a threshold. It delineates the edge not of reality itself, but of our ability to witness reality. It is the horizon of perception, the limit beyond which our instruments, our eyes, our understanding cannot reach. The darkness we see when we look into deep space is not the absence of the universe. It is the absence of our capacity to perceive what lies beyond. Consider for a moment the scale of what we are describing. If you were to begin at this very spot, at this precise location in space where you sit or stand at this moment, and if you were to travel outward in any direction, moving in a perfectly straight line through the vacuum, through the scattered debris of asteroids and the brilliant furnaces of stars and the spiral arms of galaxies, you would eventually reach a distance of approximately 46.12 billion light-years from your starting point. This measurement, this almost incomprehensible number, represents the radius of what we call the observable universe. It extends outward equally in every direction, carving out a perfect sphere of cosmic territory that we are capable, in principle, of detecting. The diameter of this sphere, the full width of this bubble of perception, measures roughly 93 billion light-years from one side to the other. To understand what this means, we must first pause and consider the nature of a light-year itself, for it is not a measure of time despite its name, but rather a measure of distance. A light-year is the distance that light, traveling through the vacuum of space at its maximum possible speed, can traverse in the time it takes for the Earth to complete one full orbit around the sunlight, moves at approximately 300,000 kilometers per second, or about 186,000 miles per second, if you prefer the older units of measurement. This velocity is not arbitrary. It is woven into the fundamental structure of space-time itself. It is a cosmic speed limit, an absolute maximum velocity that applies to all massless particles, to all electromagnetic radiation, to the propagation of causality itself. Nothing that possesses mass can reach this speed, and nothing, regardless of its properties, can exceed it. This is not merely a practical limitation imposed by engineering constraints or energy requirements. It is a foundational rule of the universe, established by the geometry of space-time as described by Einstein's theory of relativity. Because this speed is constant and universal, because it never changes regardless of the observer's own motion or the strength of gravitational fields in the vicinity, we use it as a cosmic measuring stick. We translate the vast distances between celestial objects into units of time, asking not how many kilometers or miles separate 2 points, but rather how many years it would take for light to bridge that gap. When we say that the observable universe extends 46 billion light-years in all directions, we're saying that it would take light 46 billion years to travel from the edge of that sphere to our location at its center, assuming for the moment that space itself were not expanding during that journey. Inside this sphere, within this vast bubble of observability, resides everything that human beings have ever known. Every star we have named, every galaxy we have photographed, every distant quasar whose light has been analyzed by our telescopes, every particle of cosmic dust that has left a trace in our detectors, all of it lies within this boundary. The entirety of recorded history, every civilization that has risen and fallen, every thought that has been conceived, and every emotion that has been felt, every atom that composes your body and mind, every structure from the smallest virus to the largest galactic supercluster, all of it occupies this sphere. And at the precise geometric center of this sphere, we find ourselves. Not because we are special, not because the universe has singled us out for any particular significance, but simply because we are the observers. The observable universe is by definition centered on whoever is doing the observing. It is a subjective boundary, a horizon that moves with us wherever we go. If an intelligent being on a planet orbiting a star in the Andromeda Galaxy were to map their own observable universe, they would place themselves at its center, and their bubble would overlap with ours but would not be identical to it. Some regions of space visible to them would lie beyond our horizon, and some regions visible to us would lie beyond theirs. The universe itself has no center, no privileged location, but every observer naturally finds themselves at the center of their own sphere of perception. And here we must confront something strange, something that defies our intuitive expectations about light and darkness and the appearance of the cosmos. That edge, that distant boundary separating our bubble of observable space from the infinite expanse beyond, is not actually dark. It is not black. It is not empty. In truth, it is quite the opposite. The edge of the observable universe is a wall of light, a shell of radiance that completely surrounds us, shining inward from every direction simultaneously. But this is not light as we commonly understand it. It is not the familiar white or yellow glow of stars, not the colorful emission nebulae where new suns are born, not the reflected sunlight that illuminates the planets of our solar system. This is ancient light, primordial radiation that has been traveling through space for longer than galaxies have existed, longer than atoms have existed, light that emerged from a moment so early in cosmic history that the universe itself was barely recognizable as the structure we inhabit today. Most people, when they hear the origin story of the universe, encounter a term that has become embedded in popular culture, a phrase that carries both scientific weight and a certain poetic resonance. They hear about the Big Bang. This name, coined somewhat mockingly by the astronomer Fred Hoyle, who is actually a proponent of an alternative theory, has become the standard label for the event that marks the beginning of cosmic history. But it is, as we shall explore in considerable depth, a profoundly misleading name. It conjures images of an explosion, a sudden detonation occurring at a specific point in space, a blast that sent matter hurtling outward into a pre-existing void. None of this is accurate. The Big Bang was not an explosion in any conventional sense. It did not occur at a particular location. It did not expand into empty space. These misconceptions, though widespread and persistent, represent a fundamental misunderstanding of the nature of cosmic expansion and the origin of spacetime itself. We will return to this idea repeatedly as our exploration deepens, examining it from multiple angles until the true nature of the beginning becomes clearer. But for the moment, for the purposes of understanding what lies at the edge of our observable sphere, the specific mechanism of the Big Bang is less important than simply acknowledging that this ancient light exists, that it surrounds us, that it has been traveling through space for the entire history of the universe. The reason we perceive blackness when we look toward this wall of light is rooted in the biology of human vision. Our eyes, remarkable as they are, represent only one narrow window into the electromagnetic spectrum. They have evolved to detect a specific range of wavelengths, the band of radiation that we call visible light, which happens to correspond to the peak output of our own sunday. This is not coincidental. Our eyes adapted to the light that was most abundant in our environment, allowing us to navigate our world, identify food sources, recognize threats, and communicate with others of our species. But the visible spectrum is a tiny sliver of the full electromagnetic spectrum. There are vast ranges of electromagnetic radiation, both longer and shorter than visible light, that remain completely invisible to us without the aid of technology. To understand why the ancient light at the edge of the universe is invisible to our eyes, we must think about light not as a continuous stream, but as a wave phenomenon, similar in some respects to ripples on the surface of water. Imagine a still pond, its surface perfectly smooth and undisturbed. Now, imagine dropping a small stone into that pond. At the moment of impact, the stone displaces water, pushing it outward in all directions. This creates a disturbance that propagates across the surface as a series of concentric rings, waves that travel away from the point of impact at a constant speed. Near the center, where the stone entered the water, these waves are tight and closely spaced. The peaks and troughs are pronounced, the oscillation is rapid, and the energy of the disturbance is concentrated and visible. But as the waves spread outward, as the circle grows larger and encompasses more of the pond's surface, something inevitable happens. The energy of the initial disturbance is distributed over an ever-increasing circumference. The waves become less tightly packed. The distance between successive peaks grows longer. The amplitude of the oscillation decreases. The waves become gentler, more subtle, harder to see with the naked eye. Eventually, at some distance from the impact point, the waves may become so stretched out, so reduced in amplitude, that they are no longer visible to someone standing at the edge of the pond simply looking at the surface. But this does not mean the waves have ceased to exist. The energy is still there, still propagating outward, still carrying information about that initial stone strike. If you were to place a sensitive instrument on the surface of the water, something capable of detecting minute changes in water level or pressure, you would find that the disturbance continues far beyond the range of visible ripples. The effect persists all the way to the boundaries of the pond, growing fainter and more difficult to measure, but never quite disappearing entirely. Light behaves in a strikingly similar manner. Electromagnetic radiation, whether it manifests as radio waves or microwaves or infrared or visible light or ultraviolet or X-rays or gamma rays, all consists of oscillating electric and magnetic fields propagating through space. These oscillations have a characteristic wavelength, the distance between successive peaks or troughs in the wave pattern. And this wavelength determines the properties of the radiation, including whether it is visible to human eyes. When light is first emitted from a source, its wavelength is determined by the energy of the emission process. A very hot object emits short wavelength, high-energy radiation. A cooler object emits longer wavelength, lower energy radiation. But as light travels through expanding space, as it journeys across billions of light years through a universe that is stretching and growing larger with every passing moment, something profound happens to those waves. The expansion of space itself stretches the waves. As the fabric of space-time grows, the wavelength of any photon traveling through that space grows proportionally. This is not the Doppler effect in the traditional sense, though it produces a similar observational result. It is a consequence of the geometry of an expanding universe, a stretching of the light itself as the space through which it travels expands. The longer a photon has been traveling, the more expansion it has experienced, and the more its wavelength has been stretched. Light that was emitted in the distant past, in the early universe when space was much smaller and denser, has had its wavelength elongated by the cumulative expansion that has occurred over billions of years. If that light began its journey in the visible range, it may have been stretched into the infrared by the time it reaches us. If it began in the infrared, it may have been stretched into the microwave range. If it began in the microwave range, it may now be detectable only as radio waves. This stretching effect is precisely why we cannot see the most ancient light in the universe with our naked eyes. The wall of primordial radiation that surrounds us at the edge of the observable universe was emitted when the cosmos was extremely hot and dense, and initially it was in the form of high-energy, visible and ultraviolet light. But it has been traveling for nearly 14 billion years through an expanding universe, and during that journey, its wavelength has been stretched by a factor of more than 1,000. What was once visible light is now microwave radiation, completely invisible to human vision. When we look in the direction of this ancient boundary, our eyes detect no light at all, only the blackness of perceptual limitation. But just as the pond ripples continue beyond the range of casual observation, so too does the light at the edge of the universe continue to reach us. We simply need instruments sensitive enough to detect it. This is why we build telescopes that can observe in wavelengths beyond the visible spectrum. This is why we invest in space-based observatories and ground-based detector arrays and sophisticated sensor technology. We extend the range of our perception by constructing artificial eyes that can see what our biological eyes cannot. Consider, for example, the James Webb Space Telescope, one of the most advanced astronomical instruments ever constructed by human civilization. Launched in late 2021 and positioned at a gravitationally stable point in space far beyond Earth's orbit, this telescope was designed specifically to observe the universe in infrared wavelengths. Unlike the Hubble Space Telescope, which primarily observes in visible and ultraviolet light, the James Webb Space Telescope is equipped with sensors and mirrors optimized for the infrared portion of the spectrum. This allows it to detect light that has been redshifted by cosmic expansion, light from distant galaxies that formed in the early universe, light that would be completely invisible to Hubble or to any ground-based telescope operating in visible wavelengths. When astronomers use the James Webb Space Telescope to peer into regions of space that appear completely black to optical telescopes, they discover that the darkness is illusory. The infrared sky is alive with light. Distant galaxies that cannot be seen by any other means suddenly become visible, revealing their structure, their composition, their motion through space. The telescope can look back across vast stretches of cosmic time, detecting light that has been traveling for more than 13 billion years, light that was emitted when the universe was only a few 100 million years old, when the first stars were just beginning to ignite and the first galaxies were beginning to coalesce from the primordial gas. This capability transforms our understanding of cosmic history. It allows us to witness events that occurred in the deep past, to see the universe not as it is now, but as it was billions of years ago. Because light travels at a finite speed, because it takes time for light to cross the immense distances between galaxies, looking farther into space is equivalent to looking further back in time. When we observe a galaxy that is 10 billion light years away, we are not seeing that galaxy as it exists in the present moment. We are seeing it as it existed 10 billion years ago, when the light now reaching our telescopes first began its journey. In a very real sense, telescopes are time machines, not in the science fiction sense of allowing us to physically travel to the past, but in the more literal sense of allowing us to observe the past directly, to gather information about the state of the universe at earlier epochs. And yet, even with instruments as powerful as the James Webb Space Telescope, even with our ability to detect infrared radiation that has been traveling since the youth of the cosmos, we still cannot see all the way to the edge. Beyond even the most distant galaxies that James Webb can photograph, beyond the farthest quasars and the earliest stellar nurseries, there remains a region of space that appears black even in infrared wavelengths. The void persists. The boundary of perception has been pushed back dramatically compared to what our eyes can see, but it has not been eliminated. There is still an edge to our observational capabilities, still a horizon beyond which even our most sophisticated instruments cannot penetrate. So if even the James Webb Space Telescope, with all its technological sophistication and infrared sensitivity, cannot see the edge of the observable universe, how can we possibly know that there is light there? How can we claim that a wall of ancient radiation surrounds us if we cannot detect it with infrared sensors? The answer requires us to go deeper still into the electromagnetic spectrum, to venture into wavelengths so long and energies so low that they bear almost no resemblance to what we conventionally think of as light. We must descend from the infrared range, where wavelengths are measured in micrometers, down into the microwave range, where wavelengths are measured in millimeters or centimeters. We must look for radiation that is so thoroughly stretched by cosmic expansion that it has been transformed into something nearly unrecognizable. Microwave radiation surrounds us constantly in modern technological society. It is the same portion of the electromagnetic spectrum that we use for certain types of wireless communication, for radar systems, and yes, for heating food in microwave ovens. But the microwaves we are concerned with here have nothing to do with human technology. They are natural, pervasive, and ancient beyond measure. They come at us from every direction in the sky, from directly overhead and from the horizon, from the northern celestial pole and from the southern, from every point on the celestial sphere simultaneously. This radiation is extraordinarily faint, far too weak to be felt as heat or detected by conventional means, but with sufficiently sensitive radio receivers, instruments designed to measure the intensity and properties of microwave signals, we can capture this radiation and analyze it. What these instruments reveal is astonishing. The microwave radiation that fills the universe is not random noise. It is not static. It has structure, subtle variations in intensity and frequency that encode information about the early universe. This radiation is the cosmic microwave background, often abbreviated as CMB, and it represents the oldest light in the universe, the first electromagnetic radiation that was able to travel freely through space after the Big Bang. This is the wall of light we have been discussing, the boundary of the observable universe, but stretched by cosmic expansion into a form that renders it invisible to both our eyes and to infrared telescopes. It can only be detected by instruments specifically designed to measure microwave radiation with extraordinary precision. The discovery of the cosmic microwave background is one of the most important findings in the history of science. It was first detected in 1965 by two radio astronomers, Arno Penzias and Robert Wilson, who were working with a large horn antenna at Bell Telephone Laboratories in New Jersey. They were attempting to measure radio signals from the Milky Way, but they kept encountering a persistent source of noise in their data, a uniform background hiss that seemed to come from all directions and refused to go away no matter how they adjusted their equipment or pointed their antenna. Initially, they suspected that this might be interference from nearby radio sources or perhaps some flaw in their instrument. They even famously cleaned pigeon droppings out of the antenna, thinking that might be the source of the excess signal. But the noise persisted, unchanging and omnipresent. Eventually, they learned that theoretical physicists had predicted the existence of exactly such a signal. If the universe had indeed begun in a hot, dense state and had been expanding and cooling ever since, then there should be a residual glow of thermal radiation left over from that early hot phase, now stretched in a microwave range by billions of years of cosmic expansion. The persistent noise that Penzias and Wilson had been detecting was not a flaw or interference. It was the echo of the Big Bang itself, the first light of creation, now transformed into a faint microwave whisper that fills all of space. For this discovery, which provided crucial evidence supporting the Big Bang model of cosmology, Penzias and Wilson were awarded the Nobel Prize in Physics. Since that initial detection, the cosmic microwave background has been studied in extraordinary detail by multiple generations of instruments, each more sensitive and precise than the last. Satellites, such as the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck spacecraft have mapped the CMB across the entire sky with exquisite precision, measuring not just its average properties, but also the tiny variations in temperature and intensity from one direction to another. These measurements have transformed cosmology from a largely speculative field into a precision science, allowing us to determine fundamental properties of a universe with unprecedented accuracy. The cosmic microwave background is often visualized as a heat map, a colorful oval projection of the sky where different colors represent different temperatures or intensities of the microwave radiation. These maps typically show a modeled pattern of slightly warmer and slightly cooler regions, often rendered in false colors such as blue and yellow or red and blue to make the variations more visible to the human eye. It is crucial to understand that these colors are entirely artificial. The cosmic microwave background is not actually blue or yellow or any color at all in a visible sense. It is microwave radiation, invisible to human eyes, and the colors in these maps are simply a convenient way to represent variations in microwave intensity that would otherwise be impossible to visualize. What these maps reveal is profound. The universe is not uniform. It was never uniform, not even in its earliest moments. The cosmic microwave background shows tiny variations in temperature, fluctuations of only a few parts in 100,000. But these minute differences are extraordinarily significant. They represent the seeds of all cosmic structure, the primordial density variations that would eventually grow under the influence of gravity into the galaxies and galaxy clusters we observe today. Regions of the early universe that were slightly denser than average would exert a slightly stronger gravitational pull on their surroundings, attracting more matter and becoming progressively denser over time. Regions that were slightly less dense than average would lose matter to their denser neighbors and become progressively emptier. Over hundreds of millions of years, these tiny initial differences would be amplified into the vast cosmic web of galaxies, filaments, voids, and clusters that characterizes the large-scale structure of the universe today. The fact that the cosmic microwave background exhibits these variations, these patches of slightly different temperature, tells us that even at the very beginning of cosmic history, matter was not evenly distributed. There were already regions of higher and lower density, already the seeds of future structure embedded in the fabric of the cosmos. This observation has deep implications for our understanding of the Big Bang and the physical processes that operated in the earliest moments of cosmic time. It suggests that there were quantum fluctuations in the initial state of the universe, tiny random variations in energy density that were then stretched to cosmic scales by a brief period of exponential expansion known as inflation. These stretched quantum fluctuations became the classical density variations we observe in the cosmic microwave background, which in turn became the galaxies and stars and planets of the mature universe. In this way, the largest structures in the cosmos can be traced back to the smallest possible quantum uncertainties at the beginning of time. But beyond its role in revealing the seeds of cosmic structure, the cosmic microwave background also provides us with a means of determining the age of the universe itself. By carefully analyzing the properties of this ancient radiation, by measuring its temperature and the size and distribution of the temperature fluctuations, cosmologists can work backward to determine when this light was first emitted. The cosmic microwave background was released when the universe underwent a crucial transition known as recombination. The moment when the expanding cosmos had cooled sufficiently for protons and electrons to combine and form neutral hydrogen atoms. Before this moment, the universe was a hot, opaque plasma of charged particles and photons, with light constantly scattering off free electrons and unable to travel more than a short distance before being absorbed or deflected. After recombination, when neutral atoms formed, the universe became transparent to light for the first time, and photons could travel freely through space without constant interaction with matter. The light that was released at this moment of cosmic transparency is what we now detect as the cosmic microwave background. From detailed analysis of the CMB and its properties, combined with measurements of the expansion rate of the universe and other cosmological parameters, we have determined that recombination occurred approximately 13.8 billion years ago. This gives us the age of the universe, or more precisely, the age of the observable universe, the time that has elapsed since the Big Bang. It is worth emphasizing that this number, 13.8 billion years, is not a guess or an estimate based on theoretical speculation. It is a measurement derived from observational data with well-understood uncertainties. The precision of modern cosmology allows us to state this age to within about 1% accuracy. The universe is 13.8 billion years old, give or take 100 million years or so. And here we encounter a puzzle, a seeming contradiction that strikes at the heart of our understanding of space and time and the expansion of the universe. If the cosmic microwave background was emitted 13.8 billion years ago, and if that light has been traveling toward us ever since at the speed of light, then we might reasonably expect that the edge of the observable universe, the point from which this light originated, should be located 13.8 billion light years away from us. This would be the natural conclusion if we imagine light simply traveling through a static, unchanging space. But as we have already noted, the actual distance to the edge of the observable universe is approximately 46.12 billion light years, more than 3 times greater than the naive expectation. This discrepancy is not an error. It is not a failure of measurement or a mistake in our calculations. It is a direct consequence of the expansion of space, a demonstration that the universe does not behave like a static container through which objects move, but rather like a dynamic, evolving structure that is itself growing larger with time. To understand how light that is 13.8 billion years old can have traveled a distance of 46 billion light years, we must confront the nature of cosmic expansion and the relationship between space and the objects embedded within it. Let us return to the fundamental rule that nothing can move through space faster than light. This principle, established by Albert Einstein in his special theory of relativity published in 1905, is one of the bedrock foundations of modern physics. It states that the speed of light in a vacuum, approximately 300,000 kilometers per second, represents an absolute cosmic speed limit. No material object, no particle with mass, can be accelerated to this speed, let alone beyond it. As an object with mass approaches the speed of light, its relativistic mass increases, and the amount of energy required to accelerate it further grows without bound, approaching infinity as the velocity approaches light speed. To actually reach or exceed the speed of light would require infinite energy, which is physically impossible. This speed limit is not merely a consequence of insufficient technology or limited fuel supplies. It is built into the structure of space-time itself. Time and space are not independent entities, but are woven together into a four-dimensional continuum, and the geometry of this continuum imposes the light speed limit on all causal interactions. Information cannot propagate faster than light. Cause and effect cannot be separated by faster-than-light signals. The speed of light is the speed of causality, the rate at which influence can spread through the universe. And yet, despite this ironclad rule governing the motion of objects through space, there is a remarkable loophole. The rule applies to motion through space, but it says nothing about the motion of space itself. Space is not an object embedded in some larger arena. It is the arena. It is the stage on which cosmic events play out, and that stage is not fixed or static. The stage itself can change. It can expand, it can contract, it can warp and curve in response to the presence of matter and energy. And crucially for our purposes, when space expands, it can do so at any rate whatsoever, including rates that exceed the speed of light, without violating the principles of relativity. To visualize this, imagine a grid drawn on the surface of a rubber sheet. The intersections of the grid lines represent locations in space, and the spacing between grid lines represents distance. Now imagine that you place 2 coins on this rubber sheet, one near the center and one near the edge, each resting at a grid intersection. If you were to push one of the coins across the surface of the sheet, sliding it from one grid intersection to another, that would represent motion through space, and such motion is subject to the speed of light limit. The coin cannot move from grid point to grid point faster than light could travel across the surface of the sheet. But now imagine instead that you begin to stretch the rubber sheet itself, pulling on all its edges simultaneously so that the sheet grows larger. As the sheet expands, the grid lines spread apart. The distance between any 2 grid intersections increases, even though the coins themselves have not moved across the surface of the sheet. From the perspective of someone sitting on one of the coins and using the grid to measure distances, the other coin appears to be moving away, receding into the distance as the space between them expands. Yet neither coin is actually moving through space. They are both stationary with respect to the grid. Is the grid itself the fabric of space that is expanding? Now imagine that the rubber sheet expands at a slow, steady rate. The distance between the two coins increases gradually. But if the coins are very far apart, if there are many grid squares separating them, then even a slow rate of expansion per grid square can add up to a significant rate of separation overall. If the sheet is large enough and the expansion rate is high enough, the total rate at which the two coins separate, as measured by the increasing number of grid squares between them, can exceed the speed of light, even though no individual point on the sheet is moving faster than light relative to its immediate neighbors. This is precisely what happens in an expanding universe. Galaxies are not moving through space in the conventional sense. They are not racing through a pre-existing void like bullets shot from a gun. Rather, they are embedded in space, carried along by the expansion of space itself. Each galaxy is effectively stationary with respect to its local region of space. But the space between galaxies is growing, and this growth causes the distance between galaxies to increase over time. For nearby galaxies, where the amount of expanding space is relatively small, the recession velocity is modest and well below the speed of light. But for very distant galaxies, where there is a vast amount of space between us and them, the cumulative effect of expansion across all that space can cause the recession velocity to exceed the speed of light by a significant margin. This does not violate relativity because the galaxies are not moving through space faster than light. They are being carried apart by the expansion of space, and that expansion is not subject to the light speed limit. The distinction is subtle but crucial. If a distant galaxy were to fire a beam of light in our direction, that light would still travel through space at the speed of light, covering 300,000 kilometers per second relative to the local space through which it moves. But if space itself is expanding rapidly, then even as the light travels toward us, the space between the light and us is growing, and the light may make very little progress in closing the distance. In extreme cases, if the expansion is fast enough, light emitted from a very distant galaxy may never reach us at all, despite traveling at full light speed, because the expansion of space increases the distance faster than the light can cover it. This is the key to resolving the puzzle of how 13.8 billion-year-old light can be located 46 billion light-years away. When that light was emitted shortly after the Big Bang during the era of recombination, it began traveling toward the location that would eventually become our position in space. At that time, the distance between the emission point and our future location was much smaller than 46 billion light-years. But as the light traveled, space continued to expand, and the distance the light had to cover kept increasing. The light has been traveling for 13.8 billion years, covering a certain amount of ground at light speed, but during that same time period, the expansion of space has stretched the total distance such that the current separation between us and the point of emission is now 46 billion light-years. To further complicate matters, the expansion of the universe has not proceeded at a constant rate. In the very early universe, the expansion was extremely rapid, far faster than it is today. In the most recent several billion years, the expansion has actually been accelerating, driven by the mysterious influence of dark energy. And in the intermediate period, the expansion was decelerating as the gravitational attraction of matter tried to pull everything back together. All of these factors must be taken into account when calculating the relationship between the light travel time and the current distance to the edge of the observable universe. The full calculation requires integrating the expansion history of the universe over cosmic time, and the result is that 13.8 billion years of light travel time corresponds to a current distance of approximately 46 billion light-years. To truly grasp the implications of cosmic expansion, to understand how it shapes our observations and our understanding of the universe's history, we must journey back to the early decades of the 20th century, to a time when the very notion that the universe might be changing over time was controversial, even revolutionary. We must examine the work of the scientists who first grappled with these ideas, who wrestled with the implications of general relativity and the observations of distant galaxies, and who ultimately constructed the cosmological framework within which we now interpret the cosmos. Let us turn our attention first to Albert Einstein, a figure whose name has become synonymous with genius, whose wild hair and thoughtful expression are instantly recognizable even to those who have no familiarity with his scientific contributions. Einstein's work in the early 20th century fundamentally transformed our understanding of space, time, gravity, and the structure of physical reality. In 1905, while working as a patent clerk in Bern, Switzerland, he published a series of papers that would shake the foundations of physics, including his theory of special relativity, which established the constancy of the speed of light and the relativity of time and space for observers in uniform motion. But as revolutionary as special relativity was, it was incomplete. It dealt only with observers moving at constant velocities relative to one another and said nothing about acceleration or gravity. Over the next decade, Einstein labored to extend his theory to include gravity and accelerated motion, a task that required him to fundamentally reconceptualize the nature of gravity itself. The result was his general theory of relativity, published in 1915. General relativity describes gravity not as a force acting at a distance between massive objects, as Isaac Newton had proposed more than 2 centuries earlier, but rather as a consequence of the curvature of space-time caused by the presence of mass and energy. Massive objects like stars and planets and black holes warp the fabric of space-time around them, and other objects moving through this warped space-time follow curved paths that we perceive as gravitational attraction. In Einstein's elegant formulation, matter tells space-time how to curve, and curved space-time tells matter how to move. The mathematical framework of general relativity consists of a set of equations, now known as the Einstein field equations, that relate the curvature of space-time to the distribution of matter and energy. These equations are extraordinarily complex, involving sophisticated concepts from differential geometry and tensor calculus, and finding exact solutions to them is possible only in highly symmetric or simplified situations. But even with these mathematical challenges, general relativity made a number of concrete, testable predictions that differed from the predictions of Newtonian gravity, and these predictions were quickly confirmed by observation. The theory correctly accounted for the anomalous precession of Mercury's orbit, a small discrepancy that had puzzled astronomers for decades. It predicted that light from distant stars would be bent as it passed near the sun, an effect that was confirmed during a solar eclipse in 1919 and which catapulted Einstein to worldwide fame. But despite these successes, Einstein's theory confronted him with a profound puzzle when he attempted to apply it to the universe as a whole. If one assumes that the universe contains matter distributed more or less uniformly throughout space, and if one asks how that matter should behave under the influence of gravity according to general relativity, the answer that emerges from the equations is deeply unsettling. The universe cannot remain static. The gravitational attraction between all the matter in the universe should cause it to collapse inward, contracting over time until everything eventually piles up into a single point. A static, unchanging universe filled with matter is not a stable solution to the Einstein field equations. This conclusion disturbed Einstein, and it disturbed most of his contemporaries as well, because the prevailing view at that time was that the universe was indeed static and eternal, an unchanging arena in which stars and nebulae existed in a kind of timeless equilibrium. The idea that the universe might be evolving, that it might have a beginning or an end, struck many scientists as almost metaphysical, too close to religious or philosophical speculation and too far from the solid ground of empirical observation. Einstein was convinced that there must be some way to modify his equations to allow for a static universe. some additional term that could balance the attractive force of gravity and prevent the cosmic collapse that the mathematics seem to demand. The modification he introduced is now known as the cosmological constant, represented by the Greek letter lambda. This term appears in the Einstein field equations as an additional source of space-time curvature. But unlike the curvature caused by matter and energy, which is localized and depends on the distribution of mass, the cosmological constant represents a kind of intrinsic curvature associated with empty space itself. It acts as a repulsive force, a kind of anti-gravity that pushes space apart rather than pulling it together. If the cosmological constant is tuned to precisely the right value, its repulsive effect can exactly counterbalance the attractive force of gravity, allowing the universe to remain static indefinitely, neither expanding nor contracting. Einstein included this cosmological constant in his equations reluctantly, viewing it as an ad hoc addition needed to preserve the static universe that he and others believed must exist. He later came to regard this as one of his greatest mistakes, famously calling it his biggest blunder, though the historical record suggests that this characterization may have been somewhat exaggerated or taken out of context. Regardless of Einstein's personal feelings, the introduction of the cosmological constant represents a fascinating moment in the history of science, a case where theoretical prejudice led a great physicist to modify his equations to match preconceived notions about the universe, only for later observations to reveal that the modification, though introduced for the wrong reasons, might actually correspond to a real physical phenomenon. Because here is the crucial point that we shall explore in depth. Einstein was wrong about the static universe. Observations would soon demonstrate beyond any doubt that the universe is not static but expanding. But Einstein was right about the cosmological constant, or at least about the possibility that there exists some form of energy associated with empty space that exerts a repulsive gravitational effect. He simply did not realize it at the time, and he could not have realized it because the observational evidence needed to understand the true nature of cosmic expansion and the role of the cosmological constant would not become available until years after he first introduced the concept. The story of how we discover that the universe is expanding begins not with theoretical physics, but with observational astronomy, with patient nights spent at telescopes gathering light from distant objects, with photographs painstakingly analyzed to extract information about the positions, motions, and properties of stars and nebulae. And the central figure in this observational revolution was a man named Edwin Hubble, an astronomer working at the Mount Wilson Observatory in California in the 1920s, using what was then the largest telescope in the world, the 100-inch Hooker telescope. Edwin Hubble was not the first to point telescopes at the sky, of course, nor was he the first to notice the fuzzy patches of light that astronomers called nebulae, diffuse glowing clouds scattered among the pinpoint stars. These nebulae had been cataloged for more than a century, and many astronomers had speculated about their nature. Some believed that they were relatively nearby clouds of glowing gas within our own stellar system, perhaps regions where new stars were forming or remnants of old stars that had died. Others entertained the more radical idea that at least some of these nebulae might be distant collections of stars in their own right, vast stellar systems comparable to our own Milky Way, but located at enormous distances, so far away that individual stars could not be resolved and the entire system appeared as a single glowing smudge. This latter idea, often referred to as the island universe hypothesis, had been proposed as early as the 18th century, but remained highly controversial well into the 20th century because there was no reliable way to measure the distances to these nebulae. Without knowing how far away they were, it was impossible to determine their true size or nature. If a nebula was relatively close, it might be a small cloud of gas. If it was extremely distant, it might be an enormous galaxy. The two possibilities could not be distinguished based on appearance alone. Hubble's great contribution was to develop a method for measuring the distances to at least some of these nebulae, thereby settling the question of their nature once and for all. His method relied on a special class of stars called Cepheid variables, named after the prototype star Delta Cephei. Cepheid variables are massive, luminous stars that pulsate regularly, brightening and dimming in a periodic cycle that can range from a few days to several months depending on the individual star. The key discovery that made Cepheids useful as distance indicators was made by the astronomer Henrietta Leavitt in the early 20th century. Leavitt studied Cepheids in the Small Magellanic Cloud, a satellite galaxy of the Milky Way, and she noticed that there was a tight relationship between the period of Cepheids' pulsation and its intrinsic luminosity. Cepheids with longer periods were intrinsically brighter than Cepheids with shorter periods, and this relationship, now known as the period luminosity relation, was remarkably consistent. This discovery was transformative because it meant that if you could measure the period of Cepheid variable, you could determine its intrinsic brightness, how much light it was actually emitting. And if you knew its intrinsic brightness, and you could also measure its apparent brightness, how bright it appeared from Earth, then you could calculate how far away it must be. Objects that are intrinsically bright but appear dim must be far away. Objects that are intrinsically bright and also appear bright must be relatively close. The relationship between intrinsic brightness, apparent brightness, and distance follows a simple inverse square law. Apparent brightness decreases as the square of the distance. With Cepheids providing a measurement of intrinsic brightness, astronomers finally had a reliable tool for gauging distances to any object in which these stars could be identified. Hubble turned the 100-inch telescope toward the Andromeda Nebula, one of the brightest and largest nebulae in the sky, and began searching for Cepheid variables within it. This was painstaking work, requiring repeated observations over many nights to detect the subtle brightening and dimming of individual stars within the nebula. But Hubble succeeded. He found Cepheids in Andromeda, measured their periods, determined their intrinsic luminosities using Leavitt's period luminosity relation, and calculated the distance to the nebula based on their apparent brightnesses as seen from Earth. The result was shocking. Andromeda was not a nearby cloud of gas within the Milky Way. It was located at a distance of nearly 1 million light-years, far beyond the known boundaries of our own galaxy. At that distance, in order to appear as bright as it does, Andromeda had to be an enormous collection of stars, a galaxy in its own right, comparable in size and scale to the Milky Way. The island universe hypothesis was confirmed. The universe was vastly larger than anyone had imagined. The Milky Way was not the entirety of existence, but merely one galaxy among countless others scattered through space. This discovery alone would have secured Hubble's place in the history of science, but he was not finished. Having established that galaxies existed as distinct, distant objects, Hubble next turned his attention to measuring their motions. This required a different technique, one based not on brightness and distance, but on the properties of the light itself. Light can be analyzed with a spectrograph, an instrument that spreads light out into its component colors, creating a spectrum that reveals the wavelengths of light emitted or absorbed by the source. When astronomers examine the spectra of stars and galaxies, they see characteristic patterns of dark lines, called absorption lines, corresponding to specific wavelengths where light has been absorbed by atoms in the outer layers of the star or galaxy. Each chemical element absorbs light at particular wavelengths, creating a unique fingerprint that allows astronomers to identify the composition of distant objects. But something curious happens when a star or galaxy is moving relative to the Earth. The wavelengths of the absorption lines are shifted. If the object is moving toward us, the lines are shifted toward shorter wavelengths, toward the blue end of the spectrum, a phenomenon called blue shift. If the object is moving away from us, the lines are shifted toward longer wavelengths, toward the red end of the spectrum, a phenomenon called redshift. This is the Doppler effect applied to light, exactly analogous to the change in pitch of a siren as an ambulance drives past. Consider the ambulance example in detail. Sound is a wave that propagates through air by compressing and rarefying the air molecules, creating regions of higher and lower pressure that travel outward from the source. When an ambulance is stationary and its siren is blaring, the sound waves spread out uniformly in all directions, and an observer standing anywhere around the ambulance will hear the same pitch. But when the ambulance is moving, the situation changes. As the ambulance moves forward, it is chasing the sound waves it emitted a moment earlier. The waves in front of the ambulance are compressed together, with each successive wave crest closer to the previous one than it would be if the source were stationary. This compression shortens the wavelength and increases the frequency of the sound, which we perceive as a higher pitch. Conversely, behind the moving ambulance, the sound waves are stretched out, with each successive wave crest farther from the previous one. This stretching increases the wavelength and decreases the frequency, which we perceive as a lower pitch. An observer standing on the sidewalk as the ambulance approaches will hear a high-pitched siren as the sound waves are compressed by the ambulance's motion. Then, as the ambulance passes and begins moving away, the observer will hear a sudden drop in pitch as the sound waves are stretched out. The siren itself has not changed frequency. The ambulance is emitting the same sound continuously. But the motion of the source relative to the observer alters the wavelengths and frequencies that the observer detects. The same principle applies to light, though the mechanism is somewhat different because light does not require a medium like air to propagate. Light is an electromagnetic wave, a self-sustaining oscillation of electric and magnetic fields that can travel through the vacuum of space. When a light source is moving toward an observer, the light waves are compressed, shifting them toward shorter wavelengths and higher frequencies, toward the blue end of the spectrum. When the source is moving away, the waves are stretched, shifting them toward longer wavelengths and lower frequencies, toward the red end of the spectrum. Hubble, working with the astronomer Vesto Slipher, who had been measuring galaxy spectra for years, examined the light from numerous galaxies to determine their velocities. What they found was almost entirely redshifted light. Nearly every galaxy observed showed spectral lines shifted toward the red, indicating that they were moving away from us. Only a handful of very nearby galaxies, members of our local group, such as Andromeda, showed blue shifts, indicating that they were moving toward us due to the gravitational attraction between galaxies in close proximity. But the truly remarkable discovery came when Hubble compared the redshifts, and thus the recession velocities, of galaxies with their distances. He found a clear correlation. The farther away a galaxy was, the faster it appeared to be receding. Galaxies at greater distances were moving away from us at higher velocities. This relationship, now known as Hubble's law, can be expressed as a simple mathematical formula. The recession velocity of a galaxy is proportional to its distance. Double the distance, and the recession velocity doubles as well. Triple the distance, and the velocity triples. This observation is profound because it cannot be explained if the universe is static. If galaxies were simply moving through a fixed, unchanging space, there would be no reason for distant galaxies to be moving faster than nearby ones. Some galaxies might be moving toward us, some away, but there would be no systematic relationship between distance and velocity. The fact that such a relationship exists, and that it holds for galaxies at a wide range of distances, points to a single inescapable conclusion. The universe itself is expanding. Space is growing larger, carrying galaxies along with it. And the farther apart two galaxies are, the more space there is between them, and the faster they're being carried apart by the expansion. This discovery shattered the notion of a static universe. It rendered Einstein's cosmological constant, introduced solely to maintain a static cosmos, unnecessary for its original purpose. The universe is not static. It is dynamic, evolving, expanding. And if it is expanding now, then it must have been smaller in the past. If we imagine running the expansion backward in time, rewinding cosmic history, the universe would contract with galaxies growing closer together until eventually all of space was compressed into a much smaller volume, a state of extreme density and temperature. The logical endpoint of this backward extrapolation is the Big Bang itself, the moment when the expansion began, when space and time and matter and energy all emerged from an initial condition of nearly infinite density. The implications of cosmic expansion are difficult to overstate. They transformed cosmology from a philosophical discipline into an empirical science. They provided the first strong evidence for a cosmic origin event, a beginning to the universe. They opened up new questions about the nature of space and time and the physical processes that govern cosmic evolution. And they brought to the forefront a mystery that remains one of the central puzzles of modern physics. What is driving the expansion? What is the force or energy that causes space to grow? In the decades following Hubble's discovery, astronomers and physicists worked to refine the measurements of the expansion rate and to develop a theoretical framework for understanding it within the context of general relativity. It became clear that the expansion of the universe was not driven by an outward push from some explosion at the beginning of time, as the term Big Bang might suggest, but rather by the properties of spacetime itself, as described by Einstein's equations. The universe expands because that is what the equations of general relativity say a universe filled with matter should do, unless there is some additional force or energy to prevent it. For many decades, the expectation was that the expansion should be slowing down over time. The mutual gravitational attraction of all the matter in the universe should act as a brake on the expansion, gradually reducing the rate at which galaxies are flying apart. Depending on the total amount of matter, the expansion might slow sufficiently to eventually halt and reverse, leading to a contracting universe that would end in a big crunch, or it might slow but never quite stop, continuing forever but at an ever-decreasing rate, asymptotically approaching a state of rest. Determining which of these scenarios described our universe required measuring not just the current expansion rate, but also how that rate had changed over cosmic time. In the late 1990s, two independent teams of astronomers set out to measure the history of cosmic expansion by observing distant supernovae. Supernovae are exploding stars, and a particular type, called Type I supernovae, serve as excellent standard candles, objects whose intrinsic brightness is known or can be reliably determined, allowing their distances to be calculated from their apparent brightness. By measuring the distances to supernovae at various redshifts, and thus at various points in cosmic history, the teams could map out how the expansion rate had evolved over time. The expectation was that they would find evidence of deceleration, that the expansion had been faster in the past and had slowed over time due to gravitational braking. But the results showed the opposite. The expansion of the universe is accelerating. Distant supernovae were fainter than expected for their redshifts, indicating that they were farther away than they would be if the expansion had been decelerating. The universe is not only expanding, but it is expanding faster and faster as time goes on. This discovery, honored with the Nobel Prize in Physics in 2011, was a shock. It meant that there is some form of energy in the universe that exerts a repulsive gravitational effect, counteracting the attractive force of ordinary matter and driving an accelerated expansion. This mysterious energy has been given the name dark energy, and it appears to make up roughly 68% of the total energy content of the universe. We do not know what dark energy is. We do not understand its physical origin or its properties in detail, but its effects are unmistakable. It is causing the universe to expand at an ever-increasing rate, and it may be related to the cosmological constant that Einstein introduced and later regretted, a term representing an energy density associated with empty space itself. If dark energy is indeed equivalent to a cosmological constant, then it has some very unusual properties. Unlike matter, whose density decreases as the universe expands because a fixed amount of matter is spread over an ever larger volume, the energy density of a cosmological constant remains constant as the universe expands. Each cubic meter of space contributes the same amount of dark energy regardless of how the universe evolves. As space grows, the total amount of dark energy increases proportionally, and this growing reservoir of repulsive energy drives the acceleration. The existence of dark energy has profound implications for the future of the universe and for the ultimate fate of cosmic structure. If the acceleration continues indefinitely, as current evidence suggests it will, then the universe will expand without bound, and the rate of expansion will increase without limit. Distant galaxies will recede from us ever faster. Regions of space that are currently observable will eventually be pushed beyond our cosmic horizon, disappearing from view as the space between us and them expands faster than light can travel. The observable universe will shrink in terms of the number of galaxies it contains, even as space itself continues to grow. In the very distant future, countless billions of years from now, observers in our galaxy would look out into a sky devoid of other galaxies, with all external light sources having been carried beyond the reach of observation by accelerating expansion. The cosmos would appear lonely and empty, a stark contrast to the rich tapestry of galaxies we observe today. But let us return to the more immediate consequences of cosmic expansion, particularly as they relate to the structure and properties of the observable universe. We have established that space is expanding, that this expansion carries galaxies apart, and that the rate of expansion can exceed the speed of light over sufficiently large distances without violating relativity. We have seen how this leads to the stretching of light waves causing redshift, and how the most ancient light in the universe, the cosmic microwave background, has been stretched into the microwave portion of the spectrum. We have confronted the puzzle of how light that is 13.8 billion years old can be located 46 billion light years away, and we have seen that the resolution lies in accounting for the expansion of space during the light's journey. Now we must address a misconception that is deeply embedded in popular understanding of cosmology, a mistaken image of the Big Bang that leads to profound confusion about the nature of cosmic expansion and the structure of the universe. This is the idea that the Big Bang was an explosion that occurred at a specific location in space, a singular point from which all matter was ejected outward into a surrounding void. According to this flawed picture, the universe is like a sphere of debris expanding into empty space, with a center at the site of the original explosion and an edge where the debris peters out into nothingness. We, and all the galaxies we observe, are somewhere within this expanding sphere, and if we could look far enough, we might be able to see the edge where the explosion took place. This picture is wrong in almost every detail. The Big Bang was not an explosion in space. It was an expansion of space. It did not occur at a particular location. It occurred everywhere, at every point that exists. It did not expand into a pre-existing void. There was no void, no surrounding emptiness. All of space, or at least all of the space that we have access to observationally, underwent the expansion simultaneously. If the universe is infinite in extent, which is consistent with current observations, then it was always infinite, even at the moment of the Big Bang. What changed was not the extent of space, but the density of matter and energy within that space. An infinite universe that is hot and dense can expand to become an infinite universe that is cool and diffuse without ever requiring a boundary or a center. To understand why the Big Bang happened everywhere, consider again our rubber sheet analogy, but this time imagine the sheet extending infinitely in all directions. Now imagine that we mark a grid of points on this sheet, with each point representing a location in space and the spacing between points representing the distance between those locations. Initially, the grid points are very close together. The entire pattern is compressed with high density. Then the sheet expands uniformly, with every part of the sheet stretching at the same rate. The grid points move apart. The distance between any 2 points increases proportionally. If 2 points were initially 1 unit apart, they are now 2 units apart. If they were initially 10 units apart, they are now 20 units apart. The expansion is not centered on any particular point. There is no point that is stationary while others move away from it. Every point sees every other point moving away from it, with the recession velocity proportional to distance. This is exactly what Hubble observed for galaxies, and it is exactly what we would expect from a uniform expansion of space. From our perspective, it looks as though we are at the center of the expansion because we see all distant galaxies receding from us. But an observer on any of those distant galaxies would see exactly the same thing. They would see their own galaxy as stationary and all other galaxies, including ours, receding from them. There is no preferred center. The universe has no center, or equivalently, Every point is the center of its own observable universe. This brings us to one of the most subtle and profound aspects of cosmological observation. The fact that we are, in a very real sense, at the center of our own observable universe, even though the universe itself has no center. The observable universe is defined as the region of space from which light has had time to reach us since the Big Bang. It is a sphere centered on our location, with a radius determined by the age of the universe and the expansion history. Every observer, regardless of their location in the universe, defines their own observable universe in exactly the same way, and that observable universe is centered on them. Our observable universe is not the same as the observable universe of a distant galaxy. The two spheres overlap, but they are not identical. Some regions of space that are observable to us are not yet observable to them, and vice versa. The edge of our observable universe, the boundary marked by the cosmic microwave background, is not a physical edge in space. It is a horizon in time. It represents the earliest epoch from which light has been able to reach us. Beyond that horizon, there is undoubtedly more space, more galaxies, more structure, but we cannot observe it because light from those regions has not had sufficient time to travel to us. If we were to wait longer, the observable universe would grow as light from progressively more distant regions reached us. But because space itself is expanding, and because that expansion is accelerating, there are regions of space that will never become observable, no matter how long we wait. Light from those regions is traveling toward us, but the space between us and them is expanding so rapidly that the light can never bridge the gap. These regions lie beyond our cosmic horizon permanently, forever cut off from our observation not by any physical barrier, but by the geometry of expanding space-time. The cosmic microwave background represents a kind of ultimate observational limit, not just practically, but fundamentally. Even if we were to build detectors of unlimited sensitivity, capable of measuring electromagnetic radiation at any wavelength with perfect precision, we could not see beyond the CMB to the earlier, denser phases of the universe. The reason is that before recombination, before the formation of neutral hydrogen atoms, when the cosmic microwave background was released, the universe was opaque. It was filled with a hot plasma of protons, electrons, and photons, all interacting constantly. Photons could not travel far without scattering off a free electron and being absorbed and re-emitted in a random direction. This meant that light could not propagate freely through space. The universe was foggy, impenetrable to electromagnetic observation. Only after recombination, when electrons combined with protons to form neutral atoms, did the fog clear and the universe become transparent. The cosmic microwave background is the light that was set free at that moment, the first light that could travel across the universe without being scattered into oblivion. In principle, there are other ways to probe the pre-recombination universe using particles that do not interact strongly with matter. Neutrinos, for example, nearly massless particles that interact only weakly with ordinary matter, could travel freely through the early universe, even when it was opaque to light. There should be a cosmic neutrino background, analogous to the cosmic microwave background, consisting of neutrinos that have been traveling through space since an even earlier epoch than the CMB photons. Similarly, gravitational waves, ripples in space-time itself, could carry information about the very earliest moments of cosmic history, from epochs when the universe was far too hot and dense for any particles as we know them to exist. Detecting these relics of the primordial universe is extraordinarily challenging, but it is not impossible in principle, and such detections would open new windows into the Big Bang that go beyond what electromagnetic observations can reveal. Let us now delve more deeply into the nature of the Big Bang itself, stripping away the misleading imagery and constructing a more accurate, though inevitably more abstract, picture of the origin of the cosmos. We have established that the Big Bang was not an explosion at a point, but an expansion of space occurring everywhere simultaneously. But what does this mean physically? What was the state of the universe at the very beginning, And how did it evolve from that initial state into the cosmos we observe today? In the standard cosmological model, often called the lambda CDM model, the universe began in a state of extremely high density and temperature. We do not know how high, and we do not know precisely what the conditions were at the very instant of the Big Bang, because our current theories of physics break down under such extreme circumstances. General relativity, which describes the behavior of space-time and gravity, and quantum mechanics, which describes the behavior of particles and fields at microscopic scales, are both necessary to understand the very early universe. But these two theories are not fully compatible with each other. Combining them into a single consistent theory of quantum gravity remains one of the great unsolved problems in theoretical physics. Nevertheless, we can trace the history of the universe back to extraordinarily early times, to fractions of a second after the Big Bang, using well-tested physical theories. At these early times, the universe was unimaginably hot, with temperatures far exceeding anything that exists in the universe today, even in the cores of the most massive stars. Under these conditions, matter as we know it could not exist. There were no atoms, no nuclei, not even protons or neutrons. The universe was filled with a seething plasma of fundamental particles, quarks, gluons, electrons, photons, neutrinos, all in thermal equilibrium, constantly colliding and interacting with one another. As the universe expanded, it cooled, and as it cooled, it underwent a series of phase transitions, moments when the character of matter and the forces governing its behavior changed qualitatively. In the first microseconds after the Big Bang, quarks and gluons combined to form protons and neutrons, the building blocks of atomic nuclei, in a process called core confinement. As the universe continued to expand and cool, some of these protons and neutrons fused together to form the lightest atomic nuclei, deuterium, helium, and trace amounts of lithium, in a process called Big Bang nucleosynthesis. This occurred during the first few minutes of cosmic history and established the primordial abundances of the lightest elements, abundances that we can still measure today in the oldest stars and in regions of space that have not been enriched by later stellar processing. The agreement between the predicted and observed abundances is one of the key pieces of evidence supporting the Big Bang model. After nucleosynthesis, the universe continued to expand and cool, but for hundreds of thousands of years, it remained too hot for electrons to combine with nuclei to form neutral atoms. The cosmos was still a plasma, still opaque to light. Then, roughly 380,000 years after Big Bang, the temperature dropped to about 3,000 degrees, cool enough for electrons to be captured by protons and helium nuclei, forming neutral hydrogen and helium atoms. This is the epoch of recombination, the moment when the cosmic microwave background was released. From this point forward, the universe was transparent and structure began to form under the influence of gravity. Initially, the distribution of matter was nearly uniform, with only tiny density fluctuations imprinted by quantum processes in the very early universe. But these tiny fluctuations were enough. Regions that were slightly denser than average had a slightly stronger gravitational pull, attracting more matter and becoming progressively denser over time. Regions that were slightly less dense lost matter to their denser neighbors and became progressively emptier. This process, driven by gravitational instability, amplified the initial tiny fluctuations into larger and larger density contrasts, eventually forming the cosmic web of filaments, sheets, and voids that characterizes the large-scale structure of the universe today. Within the densest regions, matter collapsed under its own gravity to form the first stars, roughly 100 to 200 million years after the Big Bang. These first stars were massive, composed almost entirely of hydrogen and helium, with virtually no heavier elements, because no earlier generation of stars had existed to produce those elements. When these massive stars exhausted their nuclear fuel and exploded as supernovae, they seeded the surrounding space with heavier elements forged in their cores and in the violence of the explosions themselves. Subsequent generations of stars formed from gas enriched with these heavier elements, and over billions of years, the chemical composition of the universe evolved, with progressively more carbon, oxygen, nitrogen, iron, and all the other elements necessary for planets and life. Stars clustered together under gravity to form galaxies, vast collections of hundreds of billions of stars bound together by their mutual gravitational attraction. Galaxies themselves clustered into groups and clusters and superclusters, forming a hierarchical structure that extends across the entire observable universe. And throughout this process, dark energy, the mysterious repulsive force associated with empty space, has been growing in importance, gradually overcoming the attractive force of matter and driving the accelerated expansion we observe today. Now, to truly internalize the nature of the Big Bang, to understand why it was not an explosion at a point, we must think carefully about what we mean by size and density in the context of the early universe. Imagine that you are holding a sample of the early universe, a small volume of space 1 cubic centimeter in size, extracted from the cosmos as it existed just 1 second after the Big Bang. This tiny volume contains an enormous amount of energy and matter, all compressed to an extraordinarily high density. The temperature is billions of degrees. Particles are colliding with ferocious energy. This is a sample of the Big Bang, a fragment of the hot, dense state from which everything emerged. Now imagine that you have samples from every other cubic centimeter of the universe at that same moment, 1 second after the Big Bang. Each sample looks essentially identical. Each has the same density, the same temperature, the same composition, the same violent conditions. There is no sample that is special, no location that is denser or hotter than any other. The Big Bang conditions prevail everywhere, uniformly throughout all of space. If the universe is infinite, then there are an infinite number of such samples, all identical, all experiencing the Big Bang simultaneously. As time passes and the universe expands, each of these cubic centimeter samples grows larger. After 1 second, a given sample might be 2 cubic centimeters. After 2 seconds, perhaps 4 cubic centimeters. The boundaries of the sample are expanding, the volume is increasing, but the matter and energy within are being diluted as they spread over a larger region. The density decreases. The temperature drops. But every sample is undergoing exactly the same process. There is no center from which this expansion emanates. It is happening to every sample, everywhere, all at once. This is why we say the Big Bang happened everywhere. It was not a localized event, but a universal transformation, a moment when all of space simultaneously transitioned from a hot, dense state to the cooler, more diffuse state that characterizes the universe's subsequent evolution. If you were to ask where the Big Bang occurred, the answer is that it occurred at every point in space, including the point where you're sitting right now. The matter composing your body, the atoms that make up the chair you sit on, the planet beneath your feet, all of it was once part of that hot, dense plasma. Every location in the universe today corresponds to some location in the early universe, and every one of those locations was undergoing the Big Bang. To further clarify the distinction between the Big Bang as an expansion of space and an explosion in space, consider the following thought experiment. Imagine a conventional explosion, a bomb detonating in an open field. At the moment of detonation, there is a sudden release of energy at a specific location, and this energy drives debris outward in all directions at high speed. If you were to take a high-speed film of the explosion and analyze it frame by frame, you would see a clear structure. At the center, where the bomb was located, there would be a bright flash, followed by an expanding sphere of hot gas and debris. Outside this sphere, the field would be undisturbed. There would be a clear boundary between the region affected by the explosion and the region that has not yet been reached by the shock wave. If you were standing far enough away, you might see the flash of light, then hear the sound arrive moments later, and then feel the blast wave even later as the disturbance propagates outward from the central point at a finite speed. Now, imagine trying to apply this picture to the universe. If the Big Bang were an explosion at a point, we would expect to find some evidence of a center, some location where the density or temperature or expansion velocity is different from other locations, marking the site of the original detonation. We would expect to find galaxies near the center moving differently than galaxies far from the center. We would expect some preferred direction in space, some axis along which the universe looks different depending on whether we look toward the center or away from it. But we find none of this. The universe appears isotropic, meaning it looks statistically the same in all directions. The cosmic microwave background has the same average temperature everywhere on the sky, to within a few parts in 100,000. Galaxies are distributed uniformly on the largest scales, with no evidence of a central concentration or a preferred direction. The expansion rate, as measured by Hubble's law, is the same in all directions. There is no center. Furthermore, if the Big Bang were an explosion in space, there would have to be space outside the explosion into which it expands. But space and time themselves were created in the Big Bang, or more precisely, the observable portion of space and time that we have access to emerge from the Big Bang. There was no pre-existing void, no external arena. The Big Bang did not expand into anything. It was the expansion of everything, the growth of space itself, not the movement of matter through space. This leads us to confront one of the most challenging conceptual aspects of modern cosmology, the question of what, if anything, existed before the Big Bang. This question is subtle and may not even be well posed, because time itself is a feature of a universe that emerged from the Big Bang. If time began at the Big Bang, then asking what happened before the Big Bang is like asking what lies north of the North Pole. It is a category error, an attempt to apply concepts that only make sense within space-time to a situation where space-time may not have existed. Some cosmological models suggest that the Big Bang was not the absolute beginning of everything, but rather a transition from a previous state. In inflationary cosmology, for example, the universe underwent a brief period of exponential expansion in the first tiny fraction of a second after the Big Bang, driven by a special kind of energy field. This inflationary expansion smoothed out any pre-existing irregularities, stretched quantum fluctuations to cosmic scales, and set the initial conditions for the hot Big Bang phase that followed. In these models, there may have been a state before inflation, though our ability to probe or understand that state is extremely limited. Other speculative ideas, such as cyclic cosmologies, propose that the universe undergoes repeated cycles of expansion and contraction, with each Big Bang followed by a big crunch and then a new Big Bang, in an eternal sequence with no ultimate beginning or end. Still others invoke quantum cosmology, attempting to describe the origin of the universe using quantum mechanics, where the very notion of a definite beginning may be replaced by a probabilistic description of space-time emerging from a quantum state. These ideas remain largely theoretical and speculative, and it is not yet clear whether any of them can be tested observationally. What is clear is that the standard Big Bang model, extrapolated backward in time, reaches a point where densities and temperatures become so extreme that our current physical theories cannot reliably describe what is happening. This moment, often called the Planck time, occurs at approximately 10 to the negative 43 seconds after the Big Bang. At earlier times, the effects of quantum gravity become dominant, and we lack a complete theory to describe the behavior of space-time under these conditions. Understanding what happened at or before the Planck time remains one of the deepest open questions in physics. Returning to the large-scale structure of a universe and the nature of cosmic expansion, let us consider more carefully the relationship between the observable universe and the universe as a whole. The observable universe, as we have discussed, is a sphere centered on us, with a radius of approximately 46 billion light-years, encompassing all regions of space from which light has had time to reach us since the Big Bang. But this is almost certainly not the entire universe. In fact, there are strong reasons to believe that the universe extends far beyond the observable region, possibly infinitely far. One line of reasoning comes from the observation that the universe appears spatially flat, meaning that the geometry of space on large scales is consistent with Euclidean geometry, the familiar geometry of flat surfaces where parallel lines never meet and the angles of a triangle add up to exactly 180 degrees. In general relativity, The geometry of space is determined by the total energy density of a universe, including contributions from matter, radiation, and dark energy. If the total energy density is exactly equal to a critical value, space is flat. If it is greater than critical, space is positively curved, like the surface of a sphere. If it is less than critical, space is negatively curved, like the surface of a saddle. Measurements of the cosmic microwave background by satellites like Planck have determined that the universe is very close to flat, with any curvature so small that it is consistent with exactly zero within observational uncertainties. This has a remarkable implication. In general relativity, a flat, infinite space is entirely consistent with the equations, and in fact, for the universe to be flat but finite would require special conditions that seem unlikely. The simplest interpretation of the flatness of space is that the universe is infinite in extent. If so, then the observable universe is just a tiny patch, a finite bubble within an infinite cosmos, and there are vast regions of space beyond our horizon that we can never observe, but that are every bit as real as the space around us. This idea that we inhabit a finite region of perception within a possibly infinite universe has profound philosophical implications. It means that no matter how far we travel or how long we observe, we can never see the entirety of reality. There are galaxies, stars, perhaps even other civilizations that lie forever beyond our reach, not because of any technological limitation, but because of the fundamental geometry of space-time and the finite speed of light. It also means that the universe does not have a unique center or edge. Every observer, everywhere in the infinite universe, sees themselves at the center of their own observable region, surrounded by a cosmic horizon beyond which they cannot see. Now, let us return to the question of why the cosmic microwave background represents a wall of light surrounding us. We have established that this radiation is the relic of the hot, dense plasma that filled the universe roughly 380,000 years after the Big Bang, and that it has been stretched by cosmic expansion into the microwave range. But why do we observe it as coming from all directions simultaneously, forming a sphere around us? The answer lies in the geometry of space-time and the light cone structure of events in the universe. Every event in space-time, every moment at every location, has associated with it a past light cone, the collection of all events from which light could have reached that event. For us, here and now, our past light cone encompasses all the regions of space from which light has had time to reach us since the Big Bang. The boundary of this past light cone, the outermost surface, corresponds to the earliest time from which light can reach us, and that time is the epoch of recombination when the cosmic microwave background was emitted. Imagine drawing a diagram with time running vertically upward and space represented horizontally. At the bottom of the diagram, place a horizontal line representing the moment of recombination, 380,000 years after the Big Bang. At this moment, the universe becomes transparent, and light is released from every point in space. Now, from our location at the top of the diagram, representing the present day, draw lines downward at a 45-degree angle, representing the paths of light rays traveling through expanding space. These lines trace out a cone, the past light cone, and they intersect the recombination surface at a circle around us. Every point on this circle is equidistant from us in terms of light travel time, and light from all these points is reaching us right now, having traveled for 13.8 billion years through expanding space. This circle of points on the recombination surface forms the cosmic microwave background as we observe it, a shell of light surrounding us. If we were to wait a little longer, light from slightly more distant points on the recombination surface would reach us, and the observable CMB shell would grow slightly larger. But because space itself is expanding, and because the recombination surface is receding from us due to that expansion, the CMB does not grow brighter or more detailed with time. Instead, its temperature continues to decrease as the wavelengths of the photons are stretched further by ongoing expansion. The cosmic microwave background is not a static object located at a fixed distance from us. It is the light from a specific epoch in cosmic history, and different parts of that light are reaching us at different times. The CMB we observe today is not the same as the CMB observed a billion years ago, nor will it be the same as the CMB observed a billion years in the future, because we are continually receiving light from different regions of the recombination surface as time passes. It is also important to emphasize that the cosmic microwave background is not located at a specific distance of 46 billion light-years away from us, even though we often describe the edge of the observable universe as being at that distance. The CMB was emitted from locations that were much closer to us at the time of emission, roughly 42 million light-years away in moving coordinates. But those locations have since been carried to a current distance of 46 billion light-years by the expansion of space. The light has been traveling through expanding space for 13.8 billion years, covering a certain light travel distance. But the source of that light is now much farther away than the light travel distance would suggest due to the space that was created during the light's journey. These distinctions between light travel distance, moving distance, and proper distance can be confusing, but they are essential for understanding the geometry of the expanding universe. Light travel distance is simply the amount of time light has been traveling multiplied by the speed of light. It represents the distance light has covered in its journey. Moving distance is a measure that factors out the expansion of space, representing how far apart 2 points would be if we could freeze the expansion at a particular moment. Proper distance is the actual physical distance between 2 points at a given moment in cosmic time, accounting for all the expansion that has occurred up to that moment. In a static universe, these 3 measures would all be the same, but in an expanding universe, they differ, and careful attention must be paid to which one is being discussed. Let us now consider the implications of cosmic expansion for the ultimate fate of galaxies and the long-term structure of the universe. We have established that expansion is accelerating, driven by dark energy, and that distant galaxies are receding from us at speeds that increase with distance. For sufficiently distant galaxies, the recession velocity exceeds the speed of light. This has a curious consequence. Light from those galaxies can never reach us, not because the light is not traveling, but because the space between us and the source is growing faster than the light can traverse it. Imagine a photon emitted by a distant galaxy in our direction. The photon travels through space at the speed of light, covering ground toward us. But as it travels, the space between the photon and us is expanding. If the expansion is slow, the photon makes progress, gradually closing the distance despite the expansion. But if the expansion is fast enough, the photon may find itself losing ground. Even though it is traveling at full light speed, the distance between the photon and us may be increasing rather than decreasing, because space is being created between us faster than the photon can cross it. If this situation persists, the photon will never reach us. It will continue traveling indefinitely, but the expansion will always stay ahead of it, preventing it from ever crossing the gap. This defines a kind of cosmic horizon, sometimes called the event horizon of the universe, analogous in some ways to the event horizon of a black hole. Galaxies beyond this horizon are fundamentally unobservable, not just in practice, but in principle. No signal from them, no light, no information of any kind, can ever reach us because the expansion of space prevents the signal from closing the distance. As dark energy drives accelerated expansion, this horizon is moving closer to us in moving terms, meaning that galaxies that are currently observable will eventually cross the horizon and disappear from view. Over tens of billions of years, the observable universe will become progressively emptier, with fewer and fewer galaxies remaining visible as the rest are carried beyond the horizon. Eventually, in the extremely distant future, only the galaxies in our local group, the small cluster of galaxies bound together by mutual gravity, will remain visible. These galaxies are gravitationally bound, meaning that the attractive force of gravity between them is strong enough to overcome the expansion of space, keeping them together even as the rest of the universe expand away. Over time, These galaxies will merge under their own gravity, eventually forming a single large elliptical galaxy. And this single galaxy, or the evolved remnant of the Milky Way and its bound companions, will be all that remains observable. The rest of the universe will have been carried so far away by accelerating expansion that no light from external galaxies will be able to reach us. Observers in this distant future, if any exist, will look out into a dark sky devoid of galaxies, with only the stars of their own galaxy visible, and they might conclude that the universe is small, static, and lonely, unaware of the vast cosmos that once was observable but has now vanished beyond the horizon. This scenario is sometimes called the Big Freeze or heat death of the universe, one of several possible long-term fates, depending on the behavior of dark energy. If dark energy remains constant, equivalent to a cosmological constant, then the universe will continue expanding forever, cooling and diluting until all stars have burned out, all black holes have evaporated, and nothing remains but a thin, cold bath of radiation and inert matter. If dark energy grows stronger over time, as in some speculative models, the expansion could accelerate so rapidly that it eventually tears apart galaxies, then stars, then planets, then atoms themselves, in a cataclysmic event called the Big Rip. Conversely, if dark energy were to weaken or reverse, the expansion could slow or even halt and reverse, leading to a contracting universe and ultimately a big crunch. Current observations favor the first scenario, an eternal expansion with a constant or slowly varying dark energy, but the ultimate fate of the universe remains one of the great open questions in cosmology. Let us now delve deeper into the nature of the cosmic microwave background and the information it encodes about the early universe. The CMB is not perfectly uniform. It exhibits tiny temperature fluctuations, variations of about 1 part in 100,000, that are distributed across the sky in a specific pattern. These fluctuations, often called anisotropies, are visible in the detailed maps produced by satellites like COBE, WMAP, and Planck. When we analyze these maps, we find that the pattern of fluctuations is not random, but has a characteristic structure, with hot and cold spots of various sizes distributed across the sky. The pattern of fluctuations in the CMB can be decomposed into a spectrum of different angular scales, much like a musical chord can be decomposed into its constituent notes of different frequencies. This spectrum, called the angular power spectrum of the CMB, reveals a series of peaks and troughs corresponding to different physical processes in the early universe. The positions and heights of these peaks are determined by the properties of the primordial plasma at the time of recombination, including the density of ordinary matter, the density of dark matter, the density of dark energy, the expansion rate of the universe, and the amplitude and shape of the initial density fluctuations. By carefully measuring the angular power spectrum and comparing it to theoretical predictions from cosmological models, scientists can determine these fundamental parameters with remarkable precision. This is how we know, for example, that ordinary matter makes up about 5% of the total energy content of the universe. Dark matter makes up about 27%, and dark energy makes up about 68%. This is how we know that the universe is spatially flat to within a fraction of a percent. This is how we know the age of the universe, the current expansion rate, and the properties of the initial density fluctuations that seeded all cosmic structure. The agreement between the observed CMB fluctuations and the predictions of the lambda-CDM cosmological model is one of the great triumphs of modern science. It represents the culmination of decades of theoretical and observational work, transforming cosmology from a field dominated by speculation and uncertainty into a precision science with well-determined parameters and clear observational tests. The cosmic microwave background has become the single most important dataset in cosmology, a treasure trove of information about the early universe that continues to be analyzed and refined as new observations and improved analysis techniques become available. One of the most intriguing aspects of the CMB fluctuations is that they originated as quantum fluctuations in the very early universe, during the inflationary epoch that preceded the hot Big Bang phase. Inflation is a hypothetical period of exponential expansion that occurred in the first tiny fraction of a second after the Big Bang, driven by a special energy field called the inflaton. During inflation, quantum fluctuations in the inflaton field were stretched to macroscopic and eventually cosmic scales, becoming the classical density variations that we observe in the CMB and in the distribution of galaxies. In this way, the largest structures in the universe today can be traced back to quantum uncertainties at the smallest possible scales, a remarkable connection between the quantum realm and the cosmic domain. Inflation also solves several puzzles that plagued earlier versions of the Big Bang model. One puzzle is the horizon problem. Why is the cosmic microwave background so uniform across the sky, even between regions that are so far apart that light could not have traveled between them since the Big Bang? If different regions of the universe were not in causal contact, how did they manage to reach the same temperature? Inflation solves this by proposing that all the regions we see in the CMB were in close contact before inflation, achieving thermal equilibrium, and were then stretched apart by the exponential expansion. After inflation, these regions are far apart and no longer in causal contact, but they retain the same temperature because they were equilibrated before being separated. Another puzzle is the flatness problem. Why is the universe so close to spatially flat? In the standard Big Bang model, without inflation, any deviation from perfect flatness would be amplified over time, and the universe would have quickly become either strongly positively curved or strongly negatively curved. To have a nearly flat universe today would require the initial curvature to have been fine-tuned to an extraordinary degree. Inflation solves this by stretching space so much that any initial curvature is diluted to nearly zero, making the observable universe appear flat regardless of what the curvature was before inflation. These successes, along with others, have made inflation a central component of the standard cosmological model, though direct evidence for inflation remains elusive. One key prediction of inflation is that it should have produced gravitational waves, ripples in space-time, during the inflationary epoch. These primordial gravitational waves would leave a subtle imprint on the CMB, a pattern of polarization that could be detected with sufficiently sensitive instruments. Several experiments are currently searching for this signal, and its detection would provide strong confirmation of the inflationary scenario and open a new window into the physics of the very early universe. The study of the cosmic microwave background has also revealed other surprises and anomalies that hint at physics beyond the standard model. For example, there are hints of subtle asymmetries in the CMB, with one half of the sky appearing slightly different from the other half in ways that are not predicted by the simplest inflationary models. There are also hints of larger-than-expected cold spots and other features that do not fit neatly into the standard picture. It is not yet clear whether these anomalies are real signals of new physics or simply statistical flukes, artifacts of the way we analyze the data, or effects of foreground contamination from sources within our galaxy. But they remind us that our understanding of the universe, though vastly improved compared to even a few decades ago, remains incomplete, and there is still much to learn. Let us now turn our attention to the nature of dark matter, one of the most profound mysteries in modern cosmology. We have mentioned that dark matter makes up about 27% of the total energy content of the universe, far more than the ordinary matter that composes stars, planets, and human bodies. But what is dark matter? We do not know. It does not emit, absorb, or reflect light, which is why it is called dark. It interacts with ordinary matter primarily through gravity, and it is the gravitational effects of dark matter that have led us to infer its existence. The first hints of dark matter came from observations of the motions of stars and gas in galaxies. According to Newton's laws, the speed at which an object orbits in a gravitational field depends on the amount of mass interior to its orbit. For example, planets farther from the Sun orbit more slowly than planets closer to the Sun because there is no additional mass beyond the Sun's orbit to increase the gravitational pull. By analogy, we would expect that stars in the outer regions of a galaxy, far from the bright central bulge where most of the visible stars are located, should orbit more slowly than stars closer to the center. But observations show the opposite. When astronomers measure the orbital velocities of stars and gas clouds in the outer regions of spiral galaxies, they find that these objects are moving just as fast, or even faster, than objects closer to the center. This implies that there's a large amount of unseen mass distributed throughout the galaxy, extending far beyond the visible stars, and that this unseen mass is exerting a gravitational pull that keeps the outer stars moving at high speeds. This unseen mass is dark matter, and its distribution is inferred from the rotation curves of galaxies, plots of orbital velocity versus distance from the galactic center. Similar evidence for dark matter comes from observations of galaxy clusters, massive collections of hundreds or thousands of galaxies bound together by gravity. When astronomers measure the motions of individual galaxies within a cluster, they find that the galaxies are moving so fast that the cluster should fly apart, unless there is far more mass holding it together than is accounted for by the visible galaxies and gas. Again, this implies the presence of dark matter, about 5 to 10 times more dark matter than ordinary matter in a typical cluster. Even more dramatic evidence comes from gravitational lensing, the bending of light by gravity predicted by general relativity. Massive objects like galaxy clusters warp space-time around them, and light from background galaxies passing near the cluster follows a curved path through this warped space-time. This causes the images of background galaxies to be distorted, stretched into arcs and multiple images, in a pattern that depends on the distribution of mass in the cluster. By analyzing these distortions, astronomers can map the distribution of mass in the cluster, including both the visible matter and the dark matter. These maps show that dark matter is distributed more smoothly and extends over larger regions than the visible matter, forming massive halos within which the visible galaxies are embedded. The cosmic microwave background also provides evidence for dark matter. The pattern of temperature fluctuations in the CMB depends on the balance between the gravitational pull of matter trying to collapse the primordial density fluctuations and the pressure of radiation trying to push them apart. Dark matter, which does not interact with radiation, only contributes gravitational attraction and does not contribute pressure. Ordinary matter, which is coupled to radiation before recombination, contributes both gravity and pressure. The interplay between these two components leaves a distinctive signature in the CMB power spectrum, and measurements of this signature confirm that dark matter must exist and must dominate over ordinary matter in the early universe. Despite all this evidence, we do not know what dark matter is made of. It is not composed of ordinary atoms or any known particle in the standard model of particle physics. Numerous candidates have been proposed, ranging from hypothetical particles called WIMPs, weakly interacting massive particles, to axions, to primordial black holes formed in the early universe. Extensive experimental efforts are underway to detect dark matter particles directly, either by capturing rare interactions between dark matter particles and ordinary matter in ultra-sensitive detectors, or by producing dark matter particles in particle accelerators, or by detecting the products of dark matter annihilation or decay in astrophysical sources. So far, these searches have not yielded a definitive detection, and the nature of dark matter remains one of the greatest unsolved problems in physics. The existence of dark energy, the mysterious force driving the accelerated expansion of the universe, is equally puzzling. Unlike dark matter, which clumps under gravity and plays a crucial role in the formation of cosmic structure, dark energy appears to be distributed uniformly throughout space, and its density does not change significantly as the universe expands. This is very different from the behavior of ordinary matter or radiation, whose densities decrease as the universe grows and the same amount of stuff is spread over a larger volume. One possibility is that dark energy is equivalent to Einstein's cosmological constant, a constant energy density associated with the vacuum of space itself. In quantum field theory, the framework that describes the behavior of fundamental particles and forces, the vacuum is not truly empty, but is filled with fluctuating quantum fields, and these fluctuations contribute an energy density to the vacuum. In principle, This vacuum energy could act as a cosmological constant, driving accelerated expansion. However, when physicists attempt to calculate the expected value of the vacuum energy from first principles, they obtain a result that is vastly larger, by a factor of 10 to the 120th power or more, than the observed dark energy density. This enormous discrepancy, sometimes called the cosmological constant problem, is one of the most severe failures of theoretical physics and suggests that we are missing something fundamental in our understanding of the vacuum or of the relationship between quantum field theory and gravity. Other possibilities for dark energy include dynamical fields, similar to the inflaton field that drove inflation, whose energy density evolves slowly over time. These fields, sometimes called quintessence, could have properties that differ from a cosmological constant and might lead to different predictions for the future evolution of the universe. Distinguishing between a cosmological constant and dynamical dark energy requires precise measurements of how the expansion rate of the universe changes over cosmic time, observations that are at the forefront of current cosmological research. The existence of dark matter and dark energy means that the universe is far stranger and more complex than we might have imagined. Roughly 95% of the universe's energy content is in forms that we do not understand, that we cannot see directly, and that we can only infer through their gravitational effects or their influence on the expansion history. Ordinary matter, the stuff that makes up stars, planets, and living beings, constitutes only about 5% of the cosmos. We are, in a very real sense, a minor component of the universe, composed of materials that are rare on cosmic scales. This realization is humbling, but it also underscores the power of the scientific method and the ingenuity of human inquiry. Despite our limitations, despite the fact that we cannot see the vast majority of the universe's contents, we have nevertheless been able to infer their existence, measure their properties, and construct a coherent and quantitative model of cosmic evolution. We have mapped the history of the universe from the first fraction of a second after the Big Bang to the present day, a span of nearly 14 billion years. We have explained the origin of the lightest elements, the formation of the cosmic microwave background, the growth of cosmic structure, the formation of galaxies and stars, and the accelerated expansion driven by dark energy. We have connected the smallest scales, the quantum fluctuations of the early universe, to the largest scales, the distribution of galaxies across billions of light years. This is an extraordinary achievement, a testament to human curiosity and the power of reason. And yet, for all that we have learned, there remain fundamental questions that we cannot yet answer. What is the nature of dark matter? What is the nature of dark energy? What happened at the very beginning, before inflation, before the Planck time? Is our universe unique, or is it one of many in a vast multiverse? Are there other regions of space, beyond our cosmic horizon, where the laws of physics or the constants of nature are different? Will the universe expand forever, growing ever colder and emptier, or will some unexpected change in dark energy or some unknown physical process alter its fate? These questions lie at the frontier of cosmology, and answering them will require new observations, new experiments, and new theoretical insights. Upcoming telescopes, such as the Extremely Large Telescope and the Nancy Grace Roman Space Telescope, will probe the universe in unprecedented detail, mapping the distribution of galaxies, measuring the properties of distant supernovae and quasars, and searching for subtle effects that might reveal the nature of dark energy or the presence of primordial gravitational waves. Particle physics experiments, such as those at the Large Hadron Collider and in deep underground dark matter detectors, will search for new particles that might explain dark matter. Theoretical physicists will continue to develop new models of the early universe, of inflation, of quantum gravity, seeking to push the boundaries of our understanding to ever earlier times and ever more extreme conditions. In the meantime, we can contemplate the universe we have come to know, the vast, expanding, evolving cosmos that surrounds us, and marvel at the fact that we, tiny creatures on a small planet orbiting an ordinary star in an unremarkable region of space, have been able to decipher so much of its history and structure. We can look up at the night sky, at the stars scattered across the darkness, and know that we are seeing light that has traveled for years or centuries or millennia, that we are looking back in time with every glance. We can point our telescopes at distant galaxies and see them as they were billions of years ago, when the universe was younger and the structures we see today were just beginning to form. We can detect the faint microwave glow of the cosmic microwave background, the echo of the Big Bang, and extract from it a detailed picture of the universe as it was in its infancy, a mere few 100,000 years old, before the first stars had formed, before galaxies existed, when the cosmos was a hot, opaque plasma filling all of space. We are, in a profound sense, embedded in the history of the universe. The atoms that make up our bodies were forged in the cores of ancient stars, stars that lived and died billions of years ago, scattering their ashes into space in supernova explosions. These ashes, enriched with carbon and oxygen and nitrogen and iron and all the other heavy elements, mixed with clouds of primordial hydrogen and helium, and eventually collapsed under gravity to form new stars and planets, including our Sun and Earth. Every breath you take contains atoms that were once part of distant stars. Every element heavier than hydrogen and helium in your body, every atom of carbon in your DNA, every atom of calcium in your bones, every atom of iron in your blood, was created in a stellar furnace and delivered to the solar nebula from which the Earth formed. We are quite literally made of star stuff, as the astronomer Carl Sagan famously observed. This connection between the cosmos and ourselves is not merely poetic. It is a scientific fact, a consequence of the processes of nucleosynthesis in stars and of the recycling of matter through successive generations of stellar birth and death. It is also a reminder of our place in the grand scheme of things, of the fact that we are not separate from the universe, but are participants in it, products of its evolution, observers of its structure, explorers of its mysteries. And as we continue to explore, as we build more powerful telescopes and detectors, as we develop more sophisticated theories and models, we will undoubtedly uncover new surprises, new phenomena that challenge our understanding and force us to revise our picture of the cosmos. This is the nature of science, an ongoing process of discovery and refinement, an endless quest to push back the boundaries of ignorance and to deepen our comprehension of the natural world. The universe is vast beyond imagining. It is ancient beyond human timescales. It is strange beyond our intuitive grasp of reality. And yet, it is knowable through observation and reason, through mathematics and experimentation. We can probe its depths, measure its properties, and construct coherent explanations for its structure and evolution. This is the great adventure of cosmology, the quest to understand the universe as a whole, from its fiery birth in the Big Bang to its possible ultimate fate in the unimaginably distant future. As we stand at our particular moment in cosmic history, roughly 14 billion years after the Big Bang, we find ourselves in a universe that is mature but still evolving, a universe filled with galaxies and stars and planets, a universe where the conditions exist for complexity and life. This moment is special, not because the universe has singled us out, but because we are here to witness it, to contemplate it, to seek to understand it. In a cosmos governed by impersonal physical laws, we are conscious beings capable of asking questions about our origins and our destiny. This is a remarkable thing, perhaps the most remarkable thing of all. The observable universe, our sphere of perception, is only a tiny fraction of what may exist. Beyond our horizon, there may be an infinite expanse of space, filled with galaxies and structures that we can never see, that will forever remain beyond our reach. And yet, within our observable bubble, we have uncovered a universe of astonishing richness and complexity, a universe that rewards careful study with profound insights. We have learned that the blackness of space is not truly black, that the ancient light of the Big Bang surrounds us in every direction, stretched into invisibility by the expansion of space. We have learned that the universe had a beginning, that it has been expanding and cooling for nearly 14 billion years, that is filled with mysterious dark matter and dark energy that shape its evolution. We have learned that we are not at the center of the universe in any privileged sense, but that we are at the center of our own observable region, a perspective that every observer shares. These discoveries have transformed our understanding of existence itself. They have revealed a cosmos far grander and more intricate than our ancestors could have imagined, a cosmos that challenges us to think deeply about space and time, matter and energy, causality and destiny. And as we continue this journey of exploration, as we peer ever deeper into space and time, we carry with us the hope that each new discovery will bring us closer to answering the fundamental questions that have driven human inquiry since the dawn of consciousness. Where did we come from? What is the universe made of? How did it come to be? Where is it going? And what is our place within it? The answers we have found so far are both humbling and inspiring. We are small, fleeting creatures in a vast and ancient universe. Yet we are capable of understanding that universe, of tracing its history, of predicting its future, of recognizing our connection to the cosmic whole. This is the great gift of science, the realization that the universe is comprehensible, that it follows laws we can discover, that its mysteries, though deep, are not impenetrable. And as long as we continue to look up, to ask questions, to seek answers, we will continue to expand the sphere of our knowledge, pushing back the darkness of ignorance and illuminating the wonders of the cosmos that surrounds us.